This is Windows Hooks of Death, kernel attacks through user mode callbacks with Tarjay Ment.
All right. Welcome to my talk. Like I said, this is kernel attacks through user mode callbacks. First, a bit about myself. I'm a security researcher at Norman. I work as part of the malware detection team. My interests are vulnerability research, operating system internals. I've also done some past work on kernel exploitation in the context of the kernel pool, on Windows 7 specifically. I've also done some work on mitigations on for instance, trying to mitigate null pointer exploitation on Windows. So this talk is going to be about several vulnerability classes in Windows related to Windows hooks and user mode callbacks. These eventually end up being several unique classes like null pointer dereferences and use after freeze. They resulted in 44 patch privilege escalation vulnerabilities in MS11-034 back in April and MS11-054 last month. And there was also several unannounced vulnerabilities that were also patched as part of the variant discovery process. For us to understand all these bugs, we need to go into several mechanisms specific to Windows NT or the kernel itself and Win32k. So a lot of the background material is going to be on that. So this is the agenda. We'll start with a brief introduction, move on to talk about Win32k, the window manager specifically, because that's a lot. That's basically the component of Win32k that we're concerned with, and user mode callbacks. We'll look at several of the vulnerabilities. We'll look at their exploitability, and we'll also try to mitigate exploitation of some of these issues. And we'll wrap up with some conclusive remarks in the end. So just for a brief introduction to begin with. So the Windows GUI subsystem was traditionally all implemented in user mode, and this was done as a client-server process model, client being the application, the server being CSRSS. In NT 4.0, the server component was moved to kernel mode, and this was what introduced Win32k.sys. This was about 15 or 16 years ago. So today, Win32k manages both the window manager and the graphics device interface. I'll talk more about those later. So user mode callbacks allows Win32k to make calls back into user mode to operate on user mode data. And the reason it does this is to, for instance, invoke application-defined hooks, provide event notifications, or read and set properties in user mode structures. It's implemented, the mechanism itself is implemented in the NT executive, so there's an export that Win32k calls, and it's pretty much a reverse system call, so it's about the opposite of what you would expect for a system call. So, to sum up briefly, Win32k uses a global locking design in creating a thread-safe environment, or the window manager does. And this is presumably, remnants of the old subsystem design. So these callbacks actually interrupt kernel execution and thus allow Win32k structures and objects to be modified while you're executing on user mode. So if you don't sufficiently check for changes, you could have a number of different vulnerability classes, like I said earlier. So there's a few, some interesting previous work in this field. Thomas Garnier had a paper in Uninformed some years ago on local privilege escalations in Win32k. This was actually on user mode callbacks, but it was more on the validation of the data returned from the callback and not on the state of Win32k itself. There was also some interesting vulnerabilities patched in last year, the window creation vulnerabilities. And one of these actually was on changes. So the MS1032 did not was a bug where the current, or where Win32k did not sufficiently revalidate the parent of a window after a callback. So this was kind of like up the alley where this research is going. And Stefan Esser also had a talk. This is not related to Windows kernel at all, but it was a similar bug class in which he had a privileged component that made calls back into a non-privileged context, and he could change around on the privileged state. So the goals of this talk is to show how user mode callbacks, without very stringent checks, may introduce several subtle vulnerabilities. We'll also try to show how such vulnerabilities can be exploited, for instance, using pool or heap manipulation. And finally, we'll try to propose a method to generically mitigate null pointed reference vulnerabilities. So that was briefly on the contents. So we'll go over to Win32k. So like I said earlier, the older version of Win32k or Windows itself, or actually Windows in general, is a modified microkernel design, meaning that file system, network protocols, and drivers were all in kernel mode. But in NT 3.51, they followed a more pure microkernel approach on the implementation of the GUI subsystem. So this means that the window manager and GDI was implemented in user mode. And even though that might be slow in some contexts, they used a lot of optimizations like shared memory design, sharing memory between the client and the server process, and using paired threads to make the time slicing of context switching more efficient. So this is what pretty much it looks like. Back then, you had all these components in user mode, and you had a limited executive services that did the necessarily kernel processing of this components. The drawbacks of this design was that even though you had all this code in user mode, a lot of the graphics in the Windows subsystem relies on interacting with hardware. So you're still required to make calls to kernel mode. So that was one of the reasons why, hey, why don't we just do everything in kernel mode since we have to make these system calls anyway. And also, the client-server interaction, involves excessive thread and context switching. So that was one of the fundamental drawbacks of this design. And like I said, they used a shared memory between the client and the server process. So, each paired thread had to have a 64K shared memory buffer. And this, turned out to be quite high in terms of memory requirements. So in Windows NT 4.0, they moved these components, or many of the components, to kernel mode. So this eliminated the need for shared buffers and paired threads. There were way fewer thread and context switches, reduced memory requirements, but they still use some performance tricks such as caching or mapping kernel mode structures into user mode. And this is, it's good for performance, but really bad for, exploitation, or good for exploitation. In Windows NT 4.0, there's not much left in CSRSS, and today there's even less because they moved out the console as well. So Win32k is really just the kernel component of the Win32 subsystem, like the graphics subsystem. It implements the kernel side of the window manager, the graphics device interface. It provides also thunks to DirectX interfaces. And it has its own system call table. So whenever you interact with this module, you go through all of these system call tables. So on Windows 7, there's 800 entries. So the attack surface is quite large. So the window manager, its primary responsibility is to control window displays. It manages screen output, collects input from keyboard and mouse. It calls application-defined hooks, passes the messaging between applications, and it also manages the user objects, which we'll discuss later on. So this is the component that this talk focuses on. The GDI interface, or graphics device interface, manages the raw graphics output itself, So it has a library of graphics functions that all the user components call. So this includes functions for line text, figure drawing, graphics manipulation, and you also have GDI objects like brushes, pens, DCs, paths, regions, and you have APIs for video and print drivers as well. GDI is pretty slow compared to DirectX, so at some point it's probably going to be replaced. But as long as there's backwards compatibility to worry about, it's not probably going to happen anytime soon. So that was briefly on Win32k. We'll talk about the window manager. So these are, the user objects are what builds up the managing components of the Win32 subsystem. So, all user handles like windows, cursors, menus are backed by their own objects. And each of these objects has their own structures. And user objects are indexed into a handle table that is maintained by Win32k. So we'll talk about that in a few slides. All the objects, they start with a common header known as the header structure. And this holds the actual handle value and also a reference count that tracks object use. So this is one of the vulnerability classes is on the reference count, or mismanagement of the reference count. There's also additional fields defined if the object is owned by, say, a thread or a process, because then you want to know, the context pointer to the thread or process object. So all the user objects, they are indexed, like I said, into a handle table that is defined per session. So when a user logs in, he gets his own session. So, all the handle information is for a session, not tied to a desktop or anything. It's global for a user. And the pointer to this handle table is stored in a shared info structure, and you can actually get this from user mode. So you can do the user32 DLL export gshared info, and you can read the handle table from user mode. And this is also because of optimization. And each entry in the user handle table is represented by a handle entry structure. So you have a handle table with all the objects that is in use. So each of these objects is represented by this structure. So you have the pointer to the object itself. You have a pointer to the owner. And you have a type field that defines the type of the object. You have flags that define how the object is used, if it's being destroyed or similar. You have also a unique seed that they use to provide entropy to the handle value itself. And the way they do this is that they increment the seed on each free of the object or the handle table entry. This doesn't really work because the unique counter is only 16 bits, so you could easily wrap it in a few tries. So this is basically how that looks. You have the pointer to the kernel memory, or the object in the kernel memory. The one to the owner, the object type, and destroyed flags, and you can easily dump this from user mode. So user objects are stored in either the session pool, the desktop heap, or the shared heap. All of these are in kernel mode, obviously. The desktop heap and the shared heap are read-only mapped into a user address space. So any process will have that invokes the GUI subsystem will have these memory mappings set up. And this is to avoid the kernel transitions. So objects associated with a particular desktop is stored in the desktop heap, and the remaining objects are either stored in the shared heap or the session pool. So when you start a GUI application, you'll have these mappings set up. So it's quite easy to enumerate the pointers to kernel memory if you want to do exploitation or anything like that. So you have the shared section that contains the user handle table and the shared heap. And each new desktop that a thread is associated with gets its own mapping into the process. So it's pretty, yeah. And all of this is because of performance to avoid making system calls. So the shared section user mapping that contains the handle table and the shared heap is set up when you load user32.dll. So if you load library this DLL, it will notify CSRSS that will set up the mapping for the process. And the user handle table is located at the base of the shared section. And this can, like I said earlier, be obtained in at least two ways, either through the export in user32 or by calling this function to CSRSS, and then CSRSS returns the pointer to the handle table in user mode. So we can easily make an application that dumps all these information without any privileges or anything. So it's it's quite convenient when you work on exploitation. You get all this information for free. So the desktop heap user mapping is set up for each thread. So Win32k maps the associated desktop heap into the user mode process whenever you invoke a new desktop or create a new desktop. The information about the desktop heap is stored in its own structure, so you get the kernel address of the desktop heap from user mode as well. And the reason they do this is to compute the address of the user mode location of these objects. So they take the pointer to the desktop heap in the kernel, and they use a delta that is also readable from user mode, and then they know the address of the user mode mapping, because they don't store pointers to user mode, they only store pointers to kernel mode, so that's why you see all these kernel mode pointers when you poke around in the desktop heap. So for them to look up other objects, they do this to find the right location in user mode. So again, we can do more. We can look up objects. We can inspect them. We can see the window procedures, the lock count of the head structure, etc. So I'll demo this later on. So on Windows 7, there's 21 different user object types. So there's 22, including the free type, which is 0. And this also includes the touch and gesture objects that were introduced in Windows 7. And information on all these types are stored in something known as the handle type information table. And this isn't mapped into user mode, but you can get, if you look up this table and look at the structures, you can find out the target memory location of each of these objects, and also their destroy routines. So here's the table of. This is quite convenient to us. You can see all the locality of all the objects, who's the owner. So when you know the owner, you know the additional header structures. For instance, if it's a thread structure or thread owned, it has a pointer to the thread infrastructure. If it's process owned, it has a pointer to the process infrastructure. And all of these, like I said, the session pool is not mapped into user mode, so it's the ones that we have access to is really just the desktop heap and the shared heap objects. So as you can see at the bottom, we have 2 new objects in Windows 7, the touch and gesture types. So what's interesting about the window manager is that it does not exclusively lock each of these objects. So when you try to use an object, you would think that it had some mutual exclusion, like a dispatch header or dispatcher header on the object itself, but it locks the entire window manager. So it has a global lock whenever it operates on these objects or any of the data structures in Win32k. So when you try to operate on a global data structure, it uses an exclusive lock if write operations are involved, and otherwise it tries to use a shared lock. So obviously, if you only read from the structures, the shared lock is better because you don't have to freeze up the entire subsystem. So this was clear enough designed to be multi-threaded. No two applications on separate desktops or actually separate window stations within the same session can process their message queues simultaneously. It's not possible because of this model. So you can see here how a function typically looks like when you try to invoke a Win32k system call. The first one acquires a share lock, while the second one acquires a exclusive lock. And although they don't say share lock, they use the term critical sections. So when they say enter shared crit, they mean that they acquired a share lock, while when you enter the user critical section, you exclusively lock this section. So that's nice. So we'll see how user mode callbacks tie into this. First, I'll just go over what user mode callbacks actually are. So in interacting with user mode data, Win32k is required to make calls back into user mode. And this led to the concept of user mode callbacks. The mechanism itself is, like I said briefly in the introduction, in KE user mode callback in the NTOS kernel. And it works like a reverse system call. Although there's not a lot of research on this field, there were some good papers and blog posts, one by Ivan LeFou and by Thomas Garnier. This mechanism, although used a lot in Window Manager, it's used extensively in user object handling itself. So this is because a lot of the objects store, for instance, data in user mode. So the prototype for this function looks like this. So Win32k calls this function. It provides an API number that is the index into the callback table in user mode. So when it makes the transition back to user mode, it looks up the pointer to this table, and that table is stored in user32.dll. So this may not make much sense, but maybe this slide or the next slide will probably be better to look at. I'll just go through this first. So in a system call, a trap frame is stored on the kernel thread stack. And this is to save context. So when you return from the kernel, you want to restore those registers. So the user mode callback mechanism does the opposite. It creates a new, so this is in the kernel, it creates a new trap frame and fakes the EIP. So it sets the EIP to KI user callback dispatcher that then calls the user32 function. And it also, copies the input buffer to the user mode stack. So it's pretty straightforward. One other thing to note is that in this mechanism on Vista and Windows 7, it switches the kernel stack. On XP, it usually it expanded the kernel stack, while on Windows 7 and Vista, there were some issues with that, so they just switched it to another kernel stack, and then switch it back when you return. So here you can see the callback to the user mode callback. It looks up one of the functions. So in this case, the callback was an event callback. So it calls into the application that set this event and then executes the code that user specifies. This is done in user mode, so this is okay. And then you return back to where you left off in the kernel using NT callback return. And this, reverses sets up the original thread stack, cleans up and continues where you left off. So yeah, the NT callback return is the function that returns. I think I already said this. It also deletes the kernel callback stack upon completion, and copies the result back to the kernel thread stack. So there's some different applications of user mode callbacks. Like I mentioned in the introduction, there's use it for invoking application Windows hooks, providing event notifications, copying data from user mode or to user mode, and this is, for instance, used in DDE handling. Hooks also allow users to execute code in response to certain events. So you can say you want a hook invoked when you call a window procedure, when you create or destroy a window, when you process the keyboard or mouse input, so you can have the application be notified about all of these events. So for instance, if you create a window, you can have a CBT hook, that's a computer-based training hook, set up to inspect the properties and the orientation of the window. And you can also change around on the orientation of the window. So, this is something the application can do quite easily. And upon returning, this kernel function will complete, and then the handle is finally returned to the application. And this is where it kind of goes wrong. You have, when you return into this function, you're free to do whatever you want. And we'll look at this in the next section. So, yes, so on to the vulnerabilities. So you're probably wondering, why is callbacks bad? What about this global lock? So, the user critical section, whenever a callback is executed, the kernel leaves this section. And this is to, be able to perform other tasks while the user mode code is being executed. And upon returning from the callback, it re-enters the critical section or reacquires the global lock. And then, you have to make sure that all the objects that you had or previously referenced in this function is still in the expected state. So, you could store, before you invoke a callback, you could store a pointer to the parent of a window. So if you do a callback, change the parent, and then return, and don't sufficiently revalidate the parent of the window, you could easily, end up operating on freed memory or null pointers or whatever. There's obviously, since user mode callbacks is so tied up to how Windows works, they have to use some kind of scheme to know when callbacks may be invoked or not. So they use this function name declaration scheme. So all functions are either prefixed XXX or ZZZ. This depends on how the function may invoke a callback. So functions prefixed XXX will probably, in most cases, leave the critical section and invoke a user mode callback. In some cases, they may require a specific set of arguments, but in most cases, it probably will invoke a callback. Functions prefixed ZZZ, they will typically invoke a deferred event callback, and this is usually not a problem, except it relies on this global value GDV or GDW, deferred win event, to be something else than null. If it's null, it will also invoke a callback that's immediate. So there were some issues with the naming scheme. So not all these functions were labeled correctly. So the programmer could assume that, hey, since the callback is not invoked, I don't need to revalidate or lock these objects or anything. For patching MS11034, they also renamed some of these functions. And you can easily, locate undecorated functions by scripting in IDAPRO. Just look up, cross-reference all the functions that potentially may call K user mode callback or exit the critical section, and see if any of these functions are not decorated as they should. And it turns out that a lot of them still are not. So it's a lot of inconsistency in the naming. So when you invoke a callback and have a reference to an object, you expect that object to be valid when you return. So what you have to do is you have to lock the object. So if you remember the header, it had a lock count value, that's clock object field. So we basically need to increment that to prevent the object from being deleted. There's two ways of performing locking, and that's thread locking and assignment locking. So thread locking is usually used in the context of a thread. So you have functions like thread lock and thread unlock. If you look into this assembly, you'll usually see that these functions are inlined or at least the thread lock function is inline. So each thread lock entry is stored as a TL structure, or a thread lock structure, and stored on a list. So if the programmer forgets to unlock and the thread terminates, it will actually iterate through this list and free all the entries. So this mechanism is quite good actually, and this is how you would typically see that in Win32k. So you see that the thread lock entry is added to the thread lock list. The lock count is incremented, and then the XXX function is called that potentially may invoke a callback, and then finally the thread lock is released. So this is how it should be done. You also have assignment locking, so not all locking is performed in the context of a thread. Sometimes you want to have it in the context of a process or global to the system. So these are the functions you use for that. So if you have an initialize, so basically you store a pointer to the object somewhere, and if that pointer is already initialized, they release the existing object reference. And this function, or this functionality, does not provide the same safety net, so to speak, that thread locking does, because if a thread terminates in a callback, the thread termination code itself has to release these references individually. If they fail to do this, we might have some inconsistency in the lock counting. So any object expected to be valid after user mode callback should be locked. Any object that no longer is used by a particular component should be unlocked or released. And like I said, if you have mismanagement in either of these, it could result in either no retention, meaning that the object was released too early, or no release, meaning that the object could never be freed, or the reference count could wrap in the worst case. So it's quite easy to understand, I guess. So here you have the absent locking. The user mode function could potentially destroy the object, and then the kernel resumes execution and keeps on using that object if it doesn't check that sufficiently. So there were some few cases. There were actually, I think, about 15 or 20 vulnerabilities related to object reference counting. So in creating a window, this was actually what I showed you earlier about the CBT hook. You can adjust the orientation of a window using a CBT hook. You can also set the Z order, like the arrangement of the window on the desktop, like from top innermost to outermost, and you do this by providing a handle to the window, after which the new window handle is inserted. The problem with this function, create window X in Win32k, was that it did not sufficiently lock this object. It just obtained a reference to the pointer to this window, and then it would invoke subsequent callbacks in which you could potentially destroy this window, and then kept on using it when linking it into the C order handle list. So this is basically what that looked like. You have the function that looks up the handle value and stores the returns the kernel object pointer. It does not lock this. It just gets the kernel object pointer, stores it in a local variable. You could do a callback, destroy this window, and then this function would operate on freed memory. Here's another one. This was in keyboard layout objects. So when you load a keyboard layout object, you can optionally call this X function. And what that does is that it tries to unload a handle that you first provide. The problem with this was that Win32k did not, again, lock this handle. It simply got the pointer to the object. So you could unload that handle in a user mode callback, and then the the remaining code would operate on freed memory again. So you could easily call like unload keyboard layout function, provide a handle to this that was provided here, and then this function down here would operate on freed memory. So you also have, that was one of the vulnerability classes. There's also what I like to say or call object state validation. So all objects are assumed to be or all objects assumed to be in a certain state should always have their state validated. And this usually involves like checking for initialized pointers or checking for flags or something like that. And user mode callbacks, could alter the state of the object properties. So, a drop-down menu could no longer be active. A parent of the window has changed. If you have a DDE conversation, the partner or the opposite party could be terminated. So there's a lot of things you need to check, even though, you might think there is not much to check for. So this was for another class of vulnerabilities. I think about 10 of them were in DDE conversation state handling. So DDE, or dynamic data exchange, is the legacy protocol for passing data between applications. So Windows still supports this. And several functions did not sufficiently validate the changes that occurred after user mode callbacks. So it did not check for the pointer to the opposite party. So that pointer could possibly be null, so it would end up in a null pointer dereference. So this is basically, try to give an overview of how a DDE conversation looks. You have the client window that does the post message or get message, depending on the way this message is passed. And then it has a specific, or for certain DDE functions or messages, it does a callback to copy the data in from user mode, because all the data is stored in user mode. So it will either copy data in from user mode or copy data out from user mode when ending up to the server. So these copy data in or copy data out result in a callback, and within that callback you could destroy the opposite party. So in this case, if you do that, you would have a null pointer reference that was exploitable in most cases. We'll talk more about the exploitability after this section. Another class is on buffer reallocation. So many objects, have item arrays associated with them, and these are, dynamically sized buffers. So we have, for instance, menu item arrays, where when you insert an item, it will, for a certain threshold, it will reallocate that memory to conserve memory. This happens either when you insert or remove entries from the buffer. If you, remove all entries, it will free the buffer. And any buffer that can be reallocated in a callback, has to be checked upon return. And if you don't do this, you'll have, there's a high probability of ending up in a use after free condition. So this basically sums up where the checks need to be performed. So you get the number of item arrays, you get a pointer to the array, you look up the first item. This should actually revalidate the buffer pointer for each iteration. Then you operate on that item. You might have a user mode callback in which you could resize the array itself. And then when you return, you usually check for if there's more items. And if you don't revalidate the total number of items in the array, you can be screwed as well. So, the lack of these checks could easily end up in vulnerabilities. So there was a lot of them in menu item handling. So menus, they hold an arbitrary number of menu items. These, like I said, are stored in a dynamically sized array. And after user mode callbacks, Win32k did not in any way validate potential changes in this array. And there's no way to lock a menu item, so they couldn't do that. And any of the XXX functions operating on a menu item was potentially vulnerable. And an attacker could easily reallocate the callback or reallocate the buffer in a callback and trigger use after free. So this is how that looks. You have the menu object that you create using these standard APIs, create pop-up menu or create menu. Then you insert menu items, and on creation of these, on the first item you reserve space for 8 items. Then on the 9th you will reallocate the array to hold an additional 8 items. So this is how that will look. In this case, you can see at the bottom that it does not revalidate the pointer. It simply uses EBX or the register and assumes that no reallocation has been made. It also stores the number of items before it enters the loop, and it does not revalidate this count. So failing to do that, you could corrupt adjacent memory. This is also one of the classes, time of check to time of use. It's kind of similar to what we already talked about, but when you leave a critical section, or the critical section itself is essentially used to prevent these issues. So when you leave the critical section and invoke a callback, you have to recheck that the values are still the same. And this can be particularly dangerous in cleanup routines. So you could potentially invoke callbacks after something has been cleaned up, and then you can reinsert it. And this could end up in stale references and to objects or buffers. So here's an example of that. They check the alt tab window if that is null. If it is, it will exit. So we have to have this defined. And then later down here, if this event hook is set, it may invoke a user mode callback, and then knowing that this is not 0, it simply calls destroy window. However, we can destroy this window within the callback, so this will actually try to destroy a null pointer window object. So we map the null page and have an exploitable vulnerability. This was not really related, but it's kind of nice to just mention. So when you validate handles, you use the handle validation APIs, and these never lock the object itself. They simply just validate the handles and return the object pointers. And you should avoid generic handle validation unless the structure of the object is irrelevant. Because if you do so, you only check for the entry that it's valid and completely ignores the type. And like I said, functions that revalidate handles after callbacks may no longer operate on the same object because the uniqueness count to provide the handle entropy is only 16 bits. So, doing this, freeing and allocating sufficient amount of times, you could fool the kernel or fool Win32k into thinking that it still operates on the same handle. So here we see, this is the first one is a completely lack of validating, anything. It just gets the handle from the callback and then tries to look that up for the handle table, and does not validate the type nor the length of the handle table itself. So, and the second one is it tries to use the generic type to look up a image. So it assumes this to be a cursor object. Of course, you can provide anything. So this also may result in some exploitable bugs. So on to exploitability. So most of these issues are related to use after freeze and null pointer references. So we'll look at those. And in the case of use after freeze, we it mainly depends on the attacker's ability to manipulate either the heap or the kernel pool, the kernel heap, so to speak. I did my previous research was on the kernel pool, so if you're interested in looking up how to manipulate the kernel pool, you should read that. There's not much public information on the kernel heap, so we'll briefly just look at how that works. And for the reference, whenever you invoke a callback, you can easily hook the functions because you have the pointer stored in the PEB, so you can just replace the pointer and do whatever you like. So the kernel has a stripped-down version of the user mode heap allocator. It has RTL allocate heap, RTL free heap. These are both used by the shared and the desktop heaps. Notably, neither heaps employ any front-end allocators. So you can see this from looking up the heap base and noticing that the extended lookup is null. This was also something that Chris Valasek pointed out in his paper on the low fragmentation heap. Just briefly that if this condition was true, there was no front-end heaps. So this means that there's no low fragmentation heap or look-aside lists. So it makes it really easy to predict where allocations are made or how they're managed. Neither heaps also encode or obfuscate the management structures. And we see this from the encode mask being null. So we can easily dump the desktop heap. Since it's mapped into user mode, we can dump it from user mode or we can dump it from the kernel. So here we see all the information. We also have the commit routine, which I'll talk about in the next slide. So the blocks index points to the heap list lookup, which holds the extended lookup pointer, which is null, and that is the reason why it does not use any front-end allocators. So, all the freed memory is indexed into a single free list. It's ordered by block size, meaning it has a granularity of 8 bytes or 16, depending on the architecture. They use list hints to optimize list lookup. So since you store all the entries in the same array, you obviously have to have some additional structures to speed up the lookup. And the requested memory is always pulled from the front of the oversized heap chunk, while the remaining fragment is put back into the free list. And if the heap runs out of committed memory, it tries to extend it by calling the commit routine. So, you could easily, if you overwrite the commit routine, this was one of the attacks on the heap, user mode heap, years back. You could do this in the kernel since there's no obfuscation. Even if, there was encoding, you would be able to get the encoding key since the heap itself is mapped into user mode. So for exploiting use after free vulnerabilities, we can use Unicode strings to reallocate the memory from the user mode callback. This allows you to control the size and the contents of the heap block. So it's very flexible. The only caveat is that you cannot use word nulls, and the last 2 bytes of the string obviously has to be terminated with a null terminator. For the desktop heap, you can use set Windows text to set window text to set the text to a window. On the session pool, you can use set class long pointer, and these are really the 2 you need to worry about. The shared heap is not it's not much used. So here you see that we'll replace the object with a string, and the vulnerability, or it tries to use a pointer in the string to perform some operations. So this easily, this is easily an exploitable vulnerability since you can control, since it's a Unicode string, you can put anything really as the pointer. A lot of these bugs are, concerned with object locking, or whenever you replace the free memory, the first thing the code usually does is that it tries to lock the object or release the object. So it will use one of these pointers to perform the locking. And this really allows you to do an arbitrary increment or an arbitrary decrement. And some targets in this context would be to try to hit the type value of a handle table entry, because if the type value is a window or 1, you can decrement that to 0 and then destroy that object. And then, since the 0 type does not have a destroy function defined, it will call the null pointer. And you can map the null pointer and then control execution. You can also target APC objects. This was something that Juru mentioned in a paper. So you could decrement the asynchronous procedure call context from user mode to kernel mode. So it would execute with kernel mode privileges. This is how that will look. Here we see the unlocking the user-controlled pointer of the reallocated memory, and this is because the Win32k calls or tries to call HM assignment lock, which is the assignment locking function on the pointer that this freed memory holds, or now reallocated memory holds. There's also, like I said, null pointer vulnerabilities. These are, potentially exploitable on Windows, since you can map the null page either by using, for instance, NT-allocate virtual memory or NT-map VO file. Many null pointer vulnerabilities are concerned with window objects. So you could map the null page, fake the window object, and then set up a fake window procedure. So if you have a flag that says that window procedure is server-side or kernel mode, you would actually be able to execute or control the procedure and execute with kernel mode privileges on any subsequent message sent to that object. So this easily shows that in doing so, you'll be able to instantly get arbitrary kernel code execution. So I have a demo on this, and we'll use the window object use after free that I showed you earlier. So let's see. Just gonna boot my VM, so I don't have a snapshot to cheat or anything. Should be fast. So what we'll do is that we'll use this CBT hook to provide a Z-order handle, after which our new handle is inserted in the Z-order chain. And we will destroy this handle or this object in a subsequent callback, and then reallocate that memory to control the locking operations that are performed subsequently. So this was a bit bigger than I expected it to be, but let's just resize this. So I'll bring up 2 instances of consoles here, then run the exploit. So this is going to be partially interactive, meaning that it will pop a message box on the callbacks, so it's easier to see. So I'll do window, and then the command that I want to execute. So in this case, I want to execute calc with system. Oh, that was the wrong one, sorry. Window 10. So now we're in the CBT hook. We set up the handle to the window that we want to insert a new window after. So what I've done here is I've looked up the mapping in user mode, found the kernel pointer, and then I can use my the utility that I had some screenshots on to dump that address. So I'll just type in shared info FE A149Z8, and then the size of the object. So now you see that this is the object that we want to destroy later on. So if I click OK again, what's going to happen is that it's going to destroy this window, and then we'll hit the next callback. We'll hit the next callback, and then we'll destroy the window. So as you can see, we assigned the zeroer window in a CBT hook. We destroyed it within the callback, and then we reallocated that freed memory. So if I do this again, you see that all the strings, or the string replaced the object. What I've also done is that since this is Unicode, I can insert pretty much any object pointer that I want as long as I avoid the double nulls. So this address here actually points to the handle table entry for the window that we will exploit or decrement. So we'll decrement its type and then destroy the window to do the free type destroy function, or trigger the free type destroy function, which then tries to execute the null pointer, null type function pointer, which is null. So we map this page. I didn't mention this, but you can see at the top here that I mapped the null page for free type trampoline. So now when I click OK, something should happen.
You got the select on.
Oh, sorry. Nice. So just to see that this actually worked, there we go. We have system. So that's quite nice. So we'll move on to the next section. So this was, exploiting a fairly complex vulnerability. There's also a lot of vulnerabilities related to null pointers. So the one that I accidentally clicked earlier, on this one, was a null pointer vulnerability. So this one is, it's the same one, or it's a different one, but it does the same. It tries to, it maps the null page and executes with kernel mode privileges. So what you want to try to do is you want to try to, avoid the null page from being mapped, or try to mitigate the exploitability of some of these issues. So we'll talk briefly about mitigations. So mitigating use after free vulnerabilities is quite difficult. It's generally hard because you usually will impact performance significantly. Some approaches you could do is you could use delayed freeze. You could use dedicated free lists. You could try to isolate the strings, meaning that when you try to reallocate this memory, you have the string in a separate heap or something. You could try to track the allocations between ring transitions. So when you perform a callback, you would keep track of the memory allocations and then recheck those when you return and make sure that everything is sane. For mitigating null pointer exploitation, we can try to deny the allocation of null pointer over the null page. There's some potential ways of doing this. We could either use system call hooking, or we could modify the page table entries, or we could try to use WAD manipulation. System call hooking is not really a good solution because, for the first, it's not supported on x64 or 64-bit due to patch guard that will check the system call table. And you also want to take a more generic approach because, just hooking the function that potentially may make these calls could, end up you failing to sufficiently hook all these functions. So, there's two that I'm aware of that you can use, but, say there were some additional, or say there are some additional, and we would miss those. So. PTE modification requires the page to be mapped, so that is not very ideal since we want to avoid the null page to be mapped. So we'll look at the WAD manipulation part. So the user mode process space is described by the virtual address descriptors. and these are structured in self-balanced trees, which are binary trees. And what's neat about WADs is that they're always checked before a page table entry is created. And this is, for instance, the way that Windows implements the no-access protection. WADs are also used to secure memory, and they can be made non-deletable. So, for instance, the process environment block and the thread environment block use this feature to prevent you from deleting the mapping. It's also used on the K-user shared data section. So this is really how a WAD tree looks. You have a process object with a pointer to the WAD root, and then have a binary tree that represents all the address ranges. So what we want to do is we want to make a WAD entry for the null page to prevent that from being mapped. So I wrote a paper on this last month, and what we do here is we try to insert a crafted WAD entry that restricts null page access for both the kernel and the user. So if you have a nullity reference in the kernel, you don't want anything to be mapped. You want to have an instant access violation, and you also want the user not to be able to map that page. We avoid the deletion using the same method as the PEB and the thread environment blocks, and we set the address range from 0 to FFFFF, which is the entire lower part of Windows that is not usually used unless you start a 16-bit process. We also set the protection to no access. This gets us a long way, but there's a fundamental issue that you could still change the protection for this since you own the WAD. It's process owned. So we use a special flag to prevent memory commits. So if the memory is not actually committed, the protection cannot be changed. So this is, we go to the leftmost branch and insert the WAD in the WAD tree. And you can see how this looks, in WinDebug. You see the mapping on top holding or blocking all the attempts, or reserving all the memory in the process of this process. And looking up the PT entry for this, you see that it's not valid, so no page table entries has been created. So the results for this seem to be quite good. Calling any of the traditional APIs for allocating memory, for allocating the null page, for trying to free the null page or change its protection, fail. You also have the map view of section, which is another way of mapping the null page, and that also does not work. So I'll run a short demo of that as well. So, like I said, this other bug was a null pointer vulnerability, easily exploitable. So what we'll do is we'll run our driver that inserts this WAD entry on process creation. Of course, you could inject into another process, but the idea is to load this driver up on loading Windows, so you would have this mapping set up for all processes. So I need to be an admin to load the driver, obviously. So I'll hit kload, which loads the driver. I can do ktest just to see that. Actually, I'll just unload it first and run ktests. So you'll see that it attempts to map the null page. It succeeds, so it can do memory reads. Okay, it can do null page write. Okay, so that works. If I load the driver, these tests fail because we set up this WAD entry. So trying all these functions does not help you. So if I redo the exploit, it's not going to work because allocate virtual memory that I use to set up the null page mapping fails with this exe code right here. So, although it's difficult to address kernel exploitation on Windows, there's definitely some possibility of doing that. So that's about sums up the talk. I'll just do a brief conclusion. Considering the future of the Win32K subsystem, it needs a much more consistent and security-oriented design. It should not be necessary for the kernel to make calls back into user mode. Doesn't really make much sense. You should also, or Microsoft should also reconsider the performance benefit of using the shared user and kernel mode memory mappings. So mapping the desktop heap and the handle table and the shared heap into user mode, although good for performance, really helps exploitation. So limiting the information available to the users is probably a good idea. The window manager should also provide a mutual exclusion design on a per object basis, not globally lock the module itself. Because with all the multi-core architectures, this doesn't really help, so it will be better suited towards those. And this is also similar to what is already done in the NT executive or the Windows kernel itself, as well as in GDI. So, legacy components is always going to be, or probably are the most vulnerable parts of an operating system, meaning that the security was not usually designed part of the original design. Win32K is built around some very old GUI subsystem code that before you had this transition. Before you introduced Win32K.sys, they used much of the same code. So it's going to be difficult when you don't have security as part of the original design. And kernel exploitation, requires knowledge about the address space. So limiting information is important. We've seen this being done on Linux, but it's not done too much on Windows. And although difficult, mitigating Windows kernel exploitation is definitely possible. Obviously, it's harder since you don't have access to source code and you cannot really hook anything you want. So it's more difficult, but it's possible. Some guys I want to thank and greet. MSRC has been really cool about all these bugs. Appreciate that. And some good references in case you're interested in reading more. If you want to learn more about the kernel heap, you should really check out Chris Valasek's paper on the low fragmentation heap. It contains really much, all the information you need to do the manipulation and stuff. So that's it. Any questions? I guess you're all tired. There's one question back there.
You talked about validation of objects and something where you can't really use manual validation for that.
Yeah.
Are there kernel provided API functions for doing object validation, or is that something you have to do kind of on a custom per object type basis?
Yeah. So you don't validate the objects themselves. You use the handle values. So you have the handle value and you provide that to a function that returns the pointer. And what that function does is that it validates it looks up the entry in the handle table, checks the type that you specify. So that is how you get the pointer from a handle. There's no way to, given that you have object pointer, there's no real way to validate that So that's why you have the lock counts and increment the lock count to ensure that that object is always valid. Okay, so thank you.